Hi, so question 1 is a 0.40 microfarads capacitor is desired. What area must the plates have if they are to be separated by a 4.0 mm air gap? And there's a second part to the question. It asks you, if now the capacitor is filled with water with K is equals to 80, find the new capacitance. Okay, so we're going to start with writing down the formula for capacitance in the case where dielectric constant is given to you. So dielectric constant are the insulators that you put in between the plates of a capacitor to increase its capacitance. So the general formula of a parallel plate capacitor is kappa, that's the dielectric constant, epsilon naught A over D. K, let's say we are doing part A of the problem, is going to be 1. This will be given to you. Dielectric constant is different for different material. So right now for the first part we have this parallel plate capacitor and there's a 4.0 mm air gap in between the plates, and for air the dielectric constant is 1. Epsilon naught has value 8.85 times 10 to the minus 12 farad meters. Always take care of the units, and we need to find the area. This is a classic example of formula based questions where you have a formula, everything is given except one thing. You plug in all the other things to get that one thing. So here capacitance is given to be 0.40 microfarads, and that is equal to 0.40 times 10 to the minus 6 farads. Okay, so it's gonna be, I'm using capacitance value here close to kappa is 1, so epsilon naught is 8.85 times 10 to the minus 12. Area, let's call that A, and D is 4.0 times 10 to the minus 3. D equals 4.0 times 10 to the minus 3 meters, because it's 4 mm, so that's 4 times 10 to the minus 3 meters. You multiply both sides by 4.0 times 10 to the minus 3, divide both sides by 8.85 times 10 to the minus 12, and if you do that, you get area to be equal to, area means A is equal to 180.8 meters square. Let's check our answer. That's correct. So see, always when you represent the answer, make sure if there's a unit that's supposed to be there, you always mention it. Okay, question 2. 3 4 microfarad capacitors are connected in series. Okay, so I look at this statement, I'm gonna make the diagram. Always make diagrams as much as you can. 3 capacitors, right, in series across a 12 volt battery. So it's gonna look like this. 3 capacitors are connected. Okay, let's call so they have equal capacitances, so I'm going to call each of those capacitance C millifarads. So it's C here, and C here, and this is V equals 12 volts. Okay, what is the total energy stored by this combination of capacitors? So if you look up in your book, and this formula will probably be given to you in exam. Energy stored in a capacitor is given by U, and its formula is charge stored divided by twice of capacitance, or when you use Q equals to CV, you get U equals half CV square. So here, if we can figure out the equivalent capacitance of, I should write down that as equivalent. In our case, it's equivalent capacitance, not C. C is already 4 millifarad. So we have to find the equivalent capacitance first. You multiply that by voltage squared divided by 2 to get your answer. So we see that these three, they are in series. So when we have a series connection, the equivalent capacitance is given by 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. This implies that 1 over C equivalent is, in our case, just 1 over C plus 1 over C plus 1 over C, and that is equals to 3 over C, or C equivalent equals to C over 3. Alright, and C is given to be 4 millifarad. This implies that C equivalent is actually equal to 4 over 3 millifarads. Now to figure out the total energy stored, you just use the formula U equals half C equivalent V square, and this will be half times 4 over 3 times 10 to the minus 3 times 12 square. And if you solve this, you should end up with 96 times 10 to the minus 3. Now the units will be joules. It will be joules because we have used everything here in SI, and in the end we have also taken care of things like millifarads, where milli is 10 to minus 3. So we just can write down this to be this. We'll check our answer. 96 millijoule. Milli is 10 to the minus 3, so our answer is correct. Question 3. In question 3, okay, it's a big one. So you've given this circuit diagram where you have, okay, which one is question? Okay, it's the one that's above it. Okay, so sorry about this. We're not supposed to consider this. So it's 25.2, right? So for the circuit given in figure 25.2, determine A, the equivalent capacitance of the circuit, and B, how much charge is stored on each capacitor if C1 equals to C2 equals to twice of C3, that is equal to 14 microfarads, and voltage across A and B is 15 volts. So I'm going to make this a little more boxy so that we can see this diagram in a more familiar way, so we can understand which ones are in series, which ones are parallel, which ones are neither in those combinations. So this is same as if you've got C1 here, right, and then there's this guy here, C2, C3, and that's A, and that's B. Okay, I'm going to copy this here, and for some reason I can't do it. Okay, I know the reason. Alright, I'm going to make that again. So got C1, C2, C3, right? So I'm solving question 3 and looking for part A. C1, C2 and C3, and we need to find the equivalent capacitance first. Capacitance. Okay, so the very first thing I see is C2 and C3 are in series, right? So if I want to replace C2 and C3 by one single effective capacitance, and let's call it effective capacitance C2, C23, so then its value is going to be 1 over C23. I'm using the formula for series combination for capacitors. It is opposite for what you have for series combinations in resistors. So it's going to be 1 over C2 plus 1 over C3, and we need to also keep in mind that C1 equals to 14 microfarads, C2 equals to 14 microfarads, and twice of C3 is equals to 14 microfarads. This implies that C3 is actually 7 microfarads. This is given in the problem. Alright, so 1 over C23 will be equal to 1 over 14 plus, we are keeping in mind that all these capacitance values are in microfarads. So C23 will also come out to be in microfarads. So C3 is 7 microfarad, and this implies that if you take the LCM, you get 1, and then you get 2, and this, when solved, will give you C23 to be equal to 14 over 3 microfarads. Okay, so that means our new circuit diagram is now this guy C1 is parallel with this guy C23, and you've got this potential difference A between some potential difference between A and B. Now next step is to recognize that C1 and C23 are in parallel. So to calculate C123, which is the equivalent capacitance of C1 and C23 being in parallel, you just add them together. So it's going to be 14 over 3, that's C23, and C1 is 14. So this will give you 3, 14 plus 14 times 3, and then C123 will be equal to 14 times 3 is 42 plus 14 over 3. Use your calculators, don't do this. 56 over 3. 56 over 3, and that is equal to, I need my calculator, 56 divided by 3, 18.66, and we were working in microfarads. Everything was in microfarads, so this is your answer for equivalent capacitance. Just want to check a few things here. Just make sure that we got this right. Okay, so 18.66 you should get 18.66 if everything's correct. So this is the value for equivalent capacitance, and the answer that is given here, I think, is in terms of C1, C2, and C3. So let's uncover that, and there you go. C1 plus, because C2 and C3 are in parallel, so that's why that's C2 C3 over C2 plus C3, and then that is added to C1 because that is in series. That is in parallel with C1. C2, C3 were in series, so that's why it's, C2 and C3 were in series, so that's why it's C2 plus C3 over C2 plus C2 times C3 over C2 plus C3. That's the equivalent capacitance between C2 and C3, and that is in parallel with C1, so you just add them together. So when you do that, you should get 18.66 microfarads. Now there's a part 2 in this problem, and part B, let's say, is how much charge is stored on each of these capacitors. Okay, charge stored on each. That is the problem that we need to solve now. So what will happen is, because there is a potential difference 15 volts between A and B, that means there's some kind of battery here. Let's make a fresh diagram for this one. Okay, so we have VAB, some battery here, VAB, and VAB is given to us to be 15 volts. Because of that, there will be current in the circuit, the capacitors will be charged. So we need to figure out what is the charge on each of these capacitors. So whenever you see a question where charge is asked on a capacitor or on different capacitors in a circuit, you need to understand two things. First, capacitors in parallel have same voltage across them, and capacitors in series have same charge. Okay, so if two capacitors are in series, the charge will be the same in both of them. If two capacitors are in parallel, then the voltage across both of them will be the same. So using those two facts, I can clearly say that charge on C2 and charge on C3 will be the same. Okay, charge on C3, let's say I'm going to call that Q3, will be same as charge on Q2. Okay, so because C2 and C3, that is, and then the effective capacitance of C2 and C3, if I make that here, this is how it was, right? C2 and C3 was here, C23 was here, and then this was A, this was B. So C23 is in parallel with C1. So that means, using the facts stated above, both of them, let's say potential difference across C23 is delta V23, will be same as potential difference across C1, and that will be equal to VAB, and that is given as 15 volts, right? So let's focus on C1 now. And also we're going to use the fact that Q2 equals to Q3, because Q2 is capacitance 2 and capacitance 3 are in series. So we have this capacitor right here, C1, voltage across it is 15 volts, right? And delta VC1 equals to 15, and capacitance value C1 is equal to 14 microfarads. This means, using the equation Q1 equals C1 V1 or Q equals CV, I can figure out the charge on this capacitor, and that will be 14 times 10 to the minus 6 times 15. If you do the math, you should get 210 microcoulomb should be the charge on this capacitor. 210. That's what we have here. Okay, now because here, if you look in this diagram, C2 and C3, they are in series, right? So when two capacitors are in series, they have the same charge. That means that look if you look at this branch, okay, I'm gonna copy. So listen carefully to what I'm gonna say now. This is really important. So this is what I have, right? And we have already established that C2 and C3, the combination of those two, is in parallel with C1, right? So for a second, just forget there's a C1 here, right? Now let's say potential across C2 is delta V2 and potential across C3 is delta V3. So we know that if you add those potential differences, that should amount to the potential difference across both of them. This is really important. Now I use again this equation, Q equals CV or V equals Q over C. So this implies that delta V2 will be Q2, charge on Q2 divided by C2. So it's going to be charge on Q2 divided by C2 plus the same way it's going to be charge on C3 divided by C3, and delta VB we already know is 15 volts. But we have already seen that because 2 and 3 are in series, charge on them will be the same. So I can replace one of these guys with other. So what will I have? I will have this, and then let's say Q3 equals to Q2, so I'm going to use it here. It's going to be 15. And if you solve this, you'll get that. Okay, let's do this. Q2, I'm going to take that as a common factor, 1 over C2, 1 over C2. So C2 is 14 and C3 is 7. So C2 is 14, C3 is 7, and this is 15. So if you do this, take the LCM, 1, I'm doing the old way, you can use the calculator if you want, 7, 2, so you get 2 here equals to 15, 3 on the top, 5, so we'll get 14 times 5, 70. And we were working in micro, so I'm going to get microcoulombs, and because Q2 equals to Q3, Q3 is also 70 microcoulombs. Let's check your answer. That's right, 70 microcoulombs. Now, question 4. A parallel plate capacitor has a capacitance of 10 microfarads and is connected with a 20 volt power supply. So you've got this capacitor is connected to a battery of 20 volts. This capacitance is given to 10 millifarad. So make sure you always draw diagrams. If you develop a habit of drawing diagrams, and if you've done enough questions, after a while you will see yourself that you will not be needing to draw any diagrams, because you can do a lot of things in your head, and that will only come from practice. But often, even if you're able to do things in your head, it's a good practice to draw diagrams, to write equations, what is given to you, what is being asked from you, those kind of things. So if you organize the information, you'll have a lot of times more things to start from, so it's a higher chance that you will be able to solve the problem. So it says that this is the situation. We have a capacitor and then there's a battery supply. So the power supply is then removed, and a dielectric with dielectric constant 4 is used to fill the space between the plates. Okay, so this is a question that is testing the knowledge whether you know what is the job of a dielectric or not. Okay, so I'm going to just tell you exactly what the job of dielectric is. A dielectric, let's say if you have a plate like this, parallel plate capacitor, so literally I've drawn two plates. Okay, one terminal here, the other terminal here. So a dielectric is any material, first of all, that is an insulator. Okay, and its job is to decrease the potential difference. Let's say initially you have this case, and then there was the potential between, that's point A and that's point B. So potential between A and B was, let's say, V. Okay, now let's say if you insert a dielectric between the two plates, so this is our final condition, F. Now I'm going to call this as V prime, right? And you insert a dielectric, that means a material between, insulating material between these plates, and every dielectric has something called dielectric constant. So you can go into discussion that's given in your book and on the internet everywhere practically as to why this happens. But what happens in the end is now the potential will be changed by a factor of this dielectric constant. So initially if the potential was V, after you have inserted a dielectric constant with a dielectric with dielectric constant kappa, the new potential difference will be earlier potential divided by kappa. So in our case we have got V initial, let's say 20 volts. So after you have inserted the dielectric, V final is going to be V initial divided by the factor, and that fact divided by the number, and that number is going to be dielectric constant, which is given to us as 4. This implies that final voltage is 5 volts. That's your answer. So you can ask questions like, let's see if that is correct. So you can ask questions like, initially dielectric constant K was filled, and before that dielectric constant K prime was filled. Let's say you initially fill it up with water, so it has some dielectric constant, and you fill it up with some oil which has some other dielectric constant. So you can ask what is the ratio of the voltage, and there will be 4 options given to you. Those kind of questions can be asked here.